Welcome to the NPA seminar. Today we're pleased to have Ben Jones from UT Arlington. Ben is a professor now.
Yeah,
a professor.
Yes.
Just making sure that it's up to date. A professor of physics at UT Arlington. He received his undergraduate degree from Cambridge University and PhD from MIT. His PhD thesis work was in IceCube, and dissertation was recognized with the Tanaka Dissertation Award from the APS. Ben's research group at UTA focuses on neutrino physics and astrophysics, in particular the nature and size of the mass of neutrino mass, development of barium tagging for the neutrinoless beta decay experiment next, and searcher for exotic phenomena such as oscillations of sterile neutrinos. He's co-chair of the Speakers and Readers Committee for the next neutrinoless beta decay collaboration, served as a co-leader of the US No Mass Process Neutrino Properties Working Group. He now works in Project 8, and he's Associate Director of the UTA Center for High Energy and Nuclear Physics and co-director of the UTA Center for Advanced Detector Technology. So he's here and tell us about the coherence, decoherence, and incoherence in neutrino oscillations. So Ben, please take it away.
Thank you very much, everybody. It's nice to be here. This talk is kind of an interesting one for me to give because I feel like I need. Does this maybe my thingy doesn't work? This is the one that does.
If you to change or
yeah, I thought we figured out the.
If you hit on the screen first, and then try it now.
It's fine. I can just press the buttons.
Okay. Yeah. Sorry about
that. Yeah. So I want to start by giving a little bit of disclaimer why I'm talking about this weird subject a little bit, because normally I work on what I would call quote unquote reasonable things, like neutrinoless double beta decay searches. I would work on next, direct neutrino mass measurements with Project 8, and high energy neutrino oscillation measurements with IceCube. This topic of neutrino coherence and decoherence and so on is something I've always had a kind of deep interest in as sort of a side gig. It started when I was in grad school and wrote this paper when I was a grad student on basically the way that the interactions between pions and their environment collapse the wave function and affect the properties of neutrino coherence. And this is a topic that's kind of gotten more interesting as more experiments have come closer to being able to actually potentially measure this. And so we recently wrote a paper on this in beta decays, and then even more recently, there's recent experimental results from BeEST that have brought this topic back up again. And not included in this list is I have a continuing friendly argument going with Dave about the details of how this might apply in simple as well. So in addition to this, there's also interesting connections between neutrino coherence and possible models of quantum gravity, which is something that we probed with IceCube, and actually our work on this on IceCube was on the cover of Nature Physics in June 2024, which was kind of nice. But I just want to mention this, that, you know, like normally I work on more reasonable things like this, and if you want to hear me talk about them, invite me again for another talk sometime. But okay, moving on to what we're going to talk about today. So we're going to talk about basically general ideas of what dictates how coherent neutrino oscillations are and how far neutrino oscillations can continue before the neutrinos become incoherent. And so there's really two parts of the talk. There's the first part is about the standard neutrino coherence, the effects that you expect to happen in the standard model. In principle, these effects are predictable from application of basic quantum mechanics. Nevertheless, despite the fact that in principle this is predictable from basic quantum mechanics, everybody still disagrees on how to apply quantum mechanics to get a prediction here. And so there's a raging controversy in the literature of which I've contributed to. And I'm going to present the parts where there's consensus and also give my perspective on the parts where there's not consensus. And I'll try and be clear which one I'm presenting at any given time. But I'll give you a picture of the state of this discussion as it applies to neutrino oscillations. Then the much shorter second part of the talk is about non-standard mechanisms of neutrino coherence loss. This is connected, like I say, to quantum gravity and the possible quantum fluctuations of the space-time metric. I'll discuss the recent measurements of this by IceCube, the advanced limits on it by 6 orders of magnitude recently, and discuss interpretations of those results in various situations. This is about 3/4 of the talk, and this is about one quarter of the talk. Okay, so neutrino oscillation. My hope is, given this is a Yale nuclear and particle astrophysics seminar, everybody knows something about what a neutrino oscillation is. This is sort of the standard picture of a neutrino oscillation. And neutrinos are emitted from a source, and they're emitted as a quantum superposition of mass states. Different mass states will travel with different momenta and hence different de Broglie wavelengths. And so you see the blue one here, which presumably is a heavier mass state, has a shorter wavelength. And so its phase is changing more quickly. And that means that after some distance, the different mass states are out of phase with each other based on the quantum evolution of their wave packets. In terms of flavor states then, what would in phase here could be said to correspond to a muon neutrino. When they get all the way out of phase, the flavor of the neutrino has changed in the flavor basis, in this case to a mixture of a muon neutrino and an electron neutrino. And the heights of these two waves here are not the same. If they were the same, that would be maximal mixing or mixing angle 45 degrees. But in fact, in nature, the amount of M1, M2, and M3 you get mixed into a given neutrino flavor state is dictated by some of these basically arbitrary parameters in the standard model, the mixing angles. And so you get this oscillation, which is an amplitude dictated by the amount of red versus the amount of blue, so how far down this dip goes in flavor, times a sinusoid in baseline divided by energy. So this is the classic picture that everybody derives in graduate classes and even undergraduate classes probably. Okay, but many have identified serious conceptual problems with this picture. So first of all, if we imagine the neutrinos are truly plane waves, a plane wave is a quantum state which is completely delocalized over all of space, which means if a neutrino is truly in a completely delocalized plane wave, that would mean it can be anywhere in the universe at any given time, and moreover have zero probability to actually be there, right? Because if you have a probability 1 integrated over all of space, then there's no probability for it to be anywhere. If a neutrino was born in a state like this, it would mean superluminal transmission of information was possible because it would be born here and then it would immediately exist over here, right? And so that would mean that the field is just immediately everywhere. Also, perfect energy and momentum of this wave means that in principle, this wave has an exact value that you can measure for m. And so no interference would be possible between these two waves if you can measure m in this wave train perfectly. And then you can also ask questions of this, false, like incorrect model, like do you pick same energy or same momentum for these waves or what? These are questions one could ask. So, I mean, a lot of this has been understood pretty early, actually, in the history of neutrino oscillations. I mean, really what happens is not that the neutrino is emitted in a completely delocalized perfect wave. It's emitted as a wave packet. And a wave packet is something like this, which travels along, and you see, still we get the interference between the different phases of the red and blue, but the whole thing is moving with a group velocity as it travels. And so I'll play it again from the beginning. So you see that now the neutrino is localized in some region of space, and you're still getting this flavor transformation as the waves get out of phase and come back into phase, right? But you remove these problems of it being completely delocalized, having superluminal transmission of information and so on and so forth, by virtue of the fact that whatever's emitting is emitting it in a finite size packet. And for neutrinos, which are very light, the velocity of this wave packet is about c, obviously. Okay, so this question let's talk about coherence, about the conditions in which you can have visible oscillation or not in this picture where neutrinos have wave packets. And there's two ways you can lose coherence. One of them is if the momentum space wave packets don't overlap with each other for the different mass states. So in that would be the case basically where you could measure m, you could measure the wave packet sufficiently narrow in momentum space that you could measure m by a sufficiently precise measurement of E and P from that wave. Now that gives you a lower limit on the P delocalization. It must be at least so wide in momentum space. And remember, the position in momentum space wave packets are Fourier transforms of each other. So it must be sufficiently wide in momentum space that you can't unambiguously know what m is in order to get an interference. And that corresponds to an upper limit on the x delocalization scale. So it must be sufficiently localized in x in that case in order to not be able to. And there's kind of this cute duality here. It turns out that this condition that you can't know the momentum and energy well enough to measure m is equivalent to saying the source must be localized in X to within one oscillation wavelength. And this criterion is kind of obvious, right? You can't see a neutrino oscillation if you don't know where the source is to within one wavelength, because you won't know where you are in the wave otherwise, right? And so these are equivalent criteria. So in a way, I think of this as kind of a trivial coherence condition, that you need to know where the source is to within one oscillation wave to be able to see an oscillation. Now, there's a more complicated one, which is a bit more subtle, which is the position space condition. In fact, these wave packets correspond to different particles with different mass, which means they move with different group velocities. And so the lighter one will outrun the heavier one, right? And so as a matter of fact, if you go far enough, these two wave packets separate. And so while they're overlapping, you can have this coherent oscillation, but by the time they've gone far enough that they've separated, then you'll end up with basically either M1 arriving or M2 arriving with whatever flavor composition they happen to arrive with. And this source of coherence loss is a lot more, let's say, controversial to understand exactly how far neutrinos have to go in order for them to lose coherence in this way. But I do want to point out that this doesn't require any exotic physics. This must happen after some distance in the standard model. It's just a question of how far you have to look before the wave packets have separated. So, I mean, we know what the group velocities of these will be because we know what the energies and masses of these states are, or at least we can know if we know the neutrino mass, we can know the velocities of this and how quickly they separate. So we know how quickly these wave trains will separate, but what we don't necessarily know from first principles is exactly how wide the wave packet is when it's born. And how far it has to go is a function of both how wide it is and how quickly they separate. And so the question of understanding the distance for neutrino coherence loss becomes a question of understanding how wide this wave packet is. So most of this first part of the talk is about a discussion of what people have done to try and understand how wide this wave packet is. And so I'm going to use pion decay as the example here because it's quite simple. It's just one particle decays to neutrino in another particle. Everything I'm going to say applies more or less to electron capture, beta decay, these other scenarios. But this will be our test case to use to develop like the intuition for the process. And so a pion decays to make a muon and a neutrino. And so the question is, based on what we understand about quantum physics, can we take this model, understand this quantum stuff, and then work out what the width of that wave packet is, right? So people have done, there's lots of papers on this topic. Some of them are pretty close to being correct, and some of them are absolute garbage, right? So you have to be careful when playing around in the literature here. But there's two papers that did make some quite interesting progress on this problem, and really, I think, have informed the way that a lot of the neutrino physics community think about the neutrino wave packets now. And it's actually become it's quite interesting talking to Dave that the people who work in the optomechanical community think about it in a very different way. But in the neutrino community, this has been very this set of papers has been very influential, and then follow-up works by Akhmedov and Smirnov based on these ideas as well. So basically, I think the first attempt to really attack this problem properly was in 2003 by Boyther, and then there's other work by Yunti and others, and then Akhmedov and Smirnov after this. So what they did is they said, okay, there's a Lagrangian that controls this decay of pion into muon and neutrino. We have some input state of the pion. We specify what happens to the muon. And if we do both those things, we specify the input state and the output state, then we can predict what state this has to be. Okay. But the problem here is that in this case, what this advance has really done has created a situation where we now have two unknowns rather than one, right? Like it was that we didn't know what this was. And now the statement is we can know what this is as long as we know what this is and what this is, right? And you may notice that there's kind of a possibility for an infinite recursion here, because now you have to know what the width of the parent is, and presumably the parent's width was created by whatever process created the parent, which involved multiple other particles. And you trace this all the way back to the beginning of the universe, and it involves every interaction of every particle in the history of time, right? So, you know, step forward or step backward, you decide. But the point is that under this model, if you specify the pion state and what the muon does, then you can know the output state. And I would say that model is the one that's the most widely held as the understanding in the neutrino oscillations community right now. Now, Personally, I have a problem with this model, which is even not even if we ignore the fact that you need infinite recursive information about the pion, there's another conceptual problem with this model, which is that it says that the oscillation probability you get for the neutrino in principle depends on what the muon does after it's produced, right? If this is measured very narrowly, it somehow collapses the wave function of this and changes the oscillations probability, right? And we have to think now at this point about the EPR experiment, right? One of the most famous thought experiments in the history of physics. This was Einstein's attempt to point out why quantum mechanics appeared to be so weird to him, basically. In the EPR experiment, just as a reminder, a source emits two entangled particles in like a fully entangled state, something like this. One goes to Alice and one goes to Bob. And Alice and Bob can choose to either measure or not measure those particles, or measure them by rotating their detectors to different angles and so on. And the thing that made Einstein feel so queasy about this is it seems like when Alice measures her particle, it collapses the wave function of Bob's one instantaneously. So that feels like something is happening like with superluminal speed, right? You measure this one, that one collapses. Of course, I mean, this is now something that everybody understands. Like what's actually happening here is you do get correlation between the results of A and B. Indeed, if Alice makes a bunch of measurements and Bob makes a bunch and they come back and compare notes, they will find there was like non-trivial entanglement between those particles, and it violates Bell's inequality. So it's beyond what you can have with classical physics or classical ignorance. But while there's correlation between the results at A and B, it's impossible to send signals between A and B. So no matter what Alice does, Bob will still get the same probability distribution of outcomes for his measurements, regardless of what Alice measures or whether she chooses to measure anything. So really the lesson from the EPR experiment is you can have correlation between the results of measurements at A and B, but it's not possible to send signals between A and B by wave function. Now, the problem with this picture from Akhmedov, Smirnov, UNT, everyone, is that this is an EPR scenario. You have two entangled particles going out. So in principle, you can get correlations between what happens here and here, but it can't be that what you do to this, whether you measure it or not, changes this if you average over all the possible outcomes of B. So we can have correlations, we can't have signaling. And the problem is that if you follow this derivation, this is the mega formula that he gets. Baked into this is a lot of details hidden in these effective parameters. This sigma effective depends on basically everything in the problem. I'm not even going to bother telling you what all these sigmas are, but they're the widths of every particle that's involved in its various detection modes. But the point is, if you drill down through the math, you find that in this picture of the neutrino coherence, the total oscillation probability will depend on what you decide to do or not do to the muon. So if you measure the entangled partner, the muon, precisely enough, you can basically shut off oscillations. And that will be true even if you integrate over all the possible fates of the muon. So danger, right? The neutrino oscillation probability, if you believe this approach, allows you to do signaling between the two final state particles in a way which is illegal, according to the EPR thought experiment. So, and this problem has permeated the literature into other places. So this is a recent paper by Akhmedov and Smirnov, which was aiming to try and explain the gallium anomaly in terms of coherence loss. And they try and drill down through all the arguments of what the coherence distances should be for neutrinos from the BeEST experiment and the gallium anomaly. And if you drill down through the paper, you eventually find the same problem that, like, they're claiming that whether or not the muon interacts or not, and how far it goes before it interacts and so on, this stuff ultimately in their picture changes the coherence properties of the neutrino. And so therefore I claim it's wrong. And so this was like a little archive battle, a kerfuffle that we had about this topic. And so, you know, just because Smirnov is famous doesn't mean he can't be wrong. So, okay, so anyway, I claim it's wrong. And you can look at the details of why in this paper, but this is the main argument, that this picture has signaling. But more than that, I mean, you can ask, where does this problem originate? Because the stuff that Voigt has done to get this looks like very reasonable quantum mechanics. He's taken a decay Lagrangian, time evolved the system, said the muon is going to end up doing something and will integrate over the things it does, right? And so that looks like a principle, like fine, but you can prove based on very simple arguments in quantum physics that this EPR thing should be valid in this situation as well. I mean, one way of proving it is by just proving that it doesn't matter which basis you use to take the trace of a density matrix to get a reduced density matrix, you get the same one no matter what trace you take, no matter what measurement is made. Actually, it's kind of interesting where the problem comes from. It's a subtle point, but the problem I claim comes from the following. So in that calculation, the statement is the muon goes out and does something and interacts with something and is measured somewhere with some width, right? Which is a pretty general statement, right? So the statement is it comes out with some p and then some width with which it's measured when it comes out, and it could do this, or it could do this, or it could do any other momentum. And then you integrate over these central momenta to get the total neutrino oscillation probability, where each one is sort of a distinct possible thing that it could have done. Now, the problem here, interestingly, is that actually this statement that it goes out into a Gaussian and it could have any central momentum and you integrate over the central momenta is actually not a legal measurement according to the postulate of quantum mechanics. Right? Quantum mechanics tells you in its postulates that the way you're allowed to make measurements is by Hermitian operators on the Hilbert space. And the Hermitian operators on the Hilbert space necessarily have orthogonal eigenstates. And these Gaussians are not orthogonal eigenstates. So integrating over these Gaussians is not equivalent to integrating over the allowed outcomes of a measurement in quantum mechanics. Which is why if you set up the problem in this way, you get these illegal signaling situations, right? You're not actually integrating over the outcomes of an allowed measurement according to quantum mechanics. Now, for handling this kind of problem, it's actually kind of helpful to go away from talking just about wave functions and talk about density matrices. If you don't already know what a density matrix is, I'm probably not going to educate you too much about it in this talk, but just as a rough idea, I mean, a wave function, a quantum state on a Hilbert space is represented by a state vector. A state which is described by a given wave function, it can be described by a density matrix. This is the case if it's a pure state. If the system has a well-defined wave function, you just put them back to back like this. But the nice thing about the density matrix is it allows you to integrate classical ignorance along with your quantum uncertainty. So this is called a mixed state, and this is a probabilistic superposition where there's a probability pi of the system being in state psi I, but these probabilities are sort of classical ignorances, whereas these are the ones encoded in here are quantum coherent uncertainties. And the reason the density matrix is so useful is that for a two-part system with parts A and B, the probability for any measurement that you apply only to B can be found from an object called the reduced density matrix for B, which is the total density matrix just summing over the allowed outcomes of measurement on A. And the thing that proof I just showed you a slide ago is basically in 4 lines, the proof that it doesn't matter which measurement you make on A, you get the same reduced density matrix for B, which basically proves the EPR thing, that you're not allowed to do signaling. And it's kind of interesting that the rho B, like, so if this is a pure state, but rho B, the reduced density matrix, will always be a mixed state in any situation where A is entangled with B. So this is like showing this principle that entanglement with unobserved systems is what generates classical probabilities, basically. Sort of the central tenet of decoherence theory, really. But okay, so what this paper in this archive kerfuffle is one of the things that we point out here is this problem that Boytha has. You can actually introduce it into the original EPR experiment if you make the same mistake. And so this is that proof I showed you before. It doesn't matter what A does, B will get the same reduced density matrix as long as A makes legal measurements. But if you let A make these measurements that have non-orthogonal final states, like the Gaussians, you then break this correspondence. So it seemed in this case, it would appear that A could send superluminal information to B if you allowed them to make that kind of a legal measurement in the EPR experiment. So my claim is that resolves that problem. So clearly that's not a good way of describing coherence of oscillations in neutrinos. So we have to try and figure out then what is the right description. And there's a few different ways of thinking about this problem that people have proposed. One way is, so some people suggest, is that you should think about this like pressure broadening. So pressure broadening is the idea that in a plasma or a gas which is emitting light, the lines that are emitted of the photons have a certain width. And interestingly, as you increase the pressure of the gas, the lines get wider and wider and wider. The reason these lines are getting wider as you increase the gas pressure is that the emission of the photons is being interrupted by collisions with the gas. So the photon can only be emitted for like this distance, the distance between the collisions. And this gives you a sort of a finite amount of time during which the emission can happen, which if you think about the Heisenberg uncertainty principle, implies a finitely wide energy width. So as you jack the pressure up, the lines get wider and wider because you're interrupting the emission more and more and more. And so there are many claims in the literature on neutrino coherence that say neutrino emission is the same kind of thing. The wave train is being interrupted as it's being emitted, and this is the sigma that's going to give you the width of the ultimate neutrino wave packet. Again, I don't agree with this picture myself. This is another thing where I would describe it as a point of controversy, but I'm giving you my picture of it. If we imagine this scenario, we have a parent which is emitting a muon and neutrino, and the parent is actually perfectly quantumly localized. So it's just traveling along like a classical thing and emitting a muon and a neutrino. That it is true that if this thing is decaying, it's emitting a neutrino wave train over this much distance, an entangled muon wave train over this much distance. And if this were actually what's limiting the quantum width of the neutrino, then you can argue that the energy uncertainty is dictated by h bar divided by the mean free path, and it will be equal for the entangled particle and for the neutrino, right? The energy uncertainty. So this is the equal energy uncertainty prescription, and it's going to be one of the models by which the BeEST collaboration interpret their data that I'll show in a minute. This is the question is this a viable way of dictating what the width of the neutrino is? Now, my claim is no, because if this parent is perfectly localized, then every piece of the neutrino wave function that goes off this way is entangled with a unique piece of the muon wave function that goes off this way. So when you take the trace over the possible final states of the muon, it will be that each possible piece of the neutrino wave function is incoherent with each other one, which will not allow coherence, right? The only time that you can break that equivalence, where measuring the muon uniquely collapses the neutrino wave function, prohibiting oscillations, is if the parent itself is finitely wide, right? If the parent itself has a finite quantum width, then it's no longer the case that a given piece of the muon wave function uniquely maps to a given piece of the neutrino wave function. And so the statement I make is that this mean free distance is actually not what's driving. You can prove this with the density matrices too, but this is just the cartoon version. This mean free distance is not what's driving neutrino oscillation coherence. It's actually to do with the delocalization scale of the parent that's doing the decay, because that's what's telling you how precisely this is encoding information about this in the final state. Okay, so enough about problems. Bring me solutions, Jones. Okay, so here's my prescription of how you should actually treat these things. My claim is what you should do. You should form the full system density matrix for the neutrino, the decay siblings, the entangled environment, and every other particle in the universe. How hard can it be? Right? Time evolve the entire universe until the neutrino production process is complete. Trace out everything else in the universe except the neutrino, and then calculate the oscillation probability with the neutrino reduced density matrix. And now, luckily, it will prove that if you set this calculation up well, you can prove that most of the things in the universe don't matter, right? But conceptually, this is what you need to do: is account for everything in the universe that may be entangled with the neutrino and trace it. When you do this, you actually get another mega formula. This is my version of the mega formula. Actually, if you stare at this, you'll find it looks very similar to the Boyka one, really. I mean, I've got the four factors of the PM&S matrix, the normal oscillation thing. But this is the term that ensures that the source is localized to well enough to less than one oscillation length. And then this term is almost the same as Boyka's term, which one? This one. But the key is, the devil is in the details. It's these sigmas, which again, in my model here, are also effective parameters that depend on a lot of things. But in this way of setting up the problem, these effective parameters only depend on parent properties, not on any acausal EPR violating possible interactions of the siblings. So really the trick is in making sure that you calculated this and you have the right description of these effective sigmas. Right? So then the question is, how do you get those effective sigmas? They depend primarily on how well localized the particle which is emitting the neutrino is, right? And various people have gotten to versions of that formula and said, okay, it depends on these things, and now we have to know the widths of those things. And the traditional approach is to wave our hands and make something up, right? And people have made up that it's the inverse mass width, the mean free path, something to do with the form factor, the length of decay region, the amount of time the experimentalist wasn't paying attention, very big, small, right? So, feel free, knock yourself out. But okay, like This is my claim about what the correct way to understand that localization scheme is. So we're going to go back to the two slit experiment here for a minute. By the way, I like to make a joke that whenever anyone tries to convince you they're right about quantum mechanics by referring to the two slit experiment, it's like when somebody tries to win an argument about politics by referring to the Nazis. You know, that means they immediately lose. But this is the way to understand it, I think, right? So, okay, we have a source that emits particles. They can go through A or B, right? And we get an interference pattern because of the when you modern square the wave function, you get a term which is like probabilistic going through A, a term which looks like the probability of going through B, and an interference term. And this is what gives us the fringes, right? In this thing. If you add an environment to this system, right, the environment starts off in state E0, and the environment may or may not be able to discern which way the particle went, right? But the environment will evolve somehow. If the particle goes through A, the environment will evolve to EA. If the particle goes through B, the environment will evolve to EB. So some evolution like this happens, right? And now the environment is in the relevant Hilbert space. So now when you take this wave function overlap, you have to do this, right? And so you've got this extra term here, which is the overlap between the environment if the particle went through A and the environment if the particle went through B. And you can think about the two limits here, right? The two limits are if EA equals EB, that means the environment didn't care which way the particle went. That means you have the fully quantum mechanical expression, that goes to 1. We just get the usual interference pattern. Or the other limit is the environment really cared which way the particle went. The overlap goes to 0. That means you get just the classical probabilities, psi A, psi A, psi B, and you get this, right? So the extent to which the environment encodes which way this went is ultimately what's going to dictate how quantum mechanically coherent this oscillation is. And the nice thing is this has actually been done, this experiment. It's a super beautiful experiment. Not exactly done with a two-slit. This is how you know my argument's valid, because it's not a two-slit interferometer. It's a Talbot-Low interferometer. That means it's right. It's been done with a Talbot-Low interferometer, which is like a set of 3 gratings that you can move around, and these buckyballs. And you get this set of interference fringes depending on the position of the gratings. When they put gas into the interferometer, the gas becomes entangled with the particles going through the interferometer. And as the pressure of the gas increases, the visibility of the interference fringes goes down. And it goes down exactly in the way you'd expect from decoherence theory. So the way the entanglement is encoding the which way information is dictating the strength of the quantum effect. And the more entanglement you have, the more classical the system is behaving and the less quantum mechanically it's behaving. So super beautiful. So this same principle can be applied to the neutrino emission system. So the question is, how do these particles that are emitting neutrinos get localized in their environments? So one way to think about this is the following. So imagine you take a particle which is just in the vacuum of space, not interacting with anything, and let it go. It will disperse. If you prepare it with a narrow wave function, that wave function will just spread out due to the Schrodinger equation. And then before you know it, that particle will just be filling the entirety of space with its wave function. The reason that particles don't end up spread all over the entire infinity of space is that while this dispersion is happening, there are also scattering interactions happening with the environment, which are localizing them, right? And encoding quantum information about them out into the wider environment. And it's actually a competition between these processes that drives the localization scales of quantum objects in their environment. And this is one of my favorite papers of all time, actually. It's a paper by Max Tegmark called Apparent Wave Function Collapse by Scattering, where he develops a systematic description of how to treat this competition and calculates the coherent widths of various particles in various environments. So like a free electron in 300 Kelvin air is localized to 1 micron, whereas a bowling ball interacting with only solar neutrinos is localized to 10 to the minus 13 meters, right? It's because a bowling ball spreads out much more slowly and also interacts much more with particles than an electron does. But you know, you can see all these are the various things that have been calculated under these set of assumptions. It's quite pretty. But so this prescription can be applied to our systems of interest for the neutrino problem. So we have a wave function of a particle which is emitting a neutrino. If the two parts of the wave function which are this far apart interact with roughly the same environment or entangle with roughly the same environment, those can oscillate. If two parts of the wave function which are further apart from each other entangle with different environments, these ones can't oscillate. Right? And so we get to this point now that resolves, I think, a lot of the arguments, right? Is a quantum system really, you have to think about it, has more than one notion of width. One notion of width is how uncertain are you about the position of that thing. And another notion of the width is how uncertain would you be about the position of that thing if you knew everything you could about all the other particles in the universe. And it's this one that dictates the coherence of neutrino oscillations. Now, luckily, those are encoded in quite an elegant way into the density matrix. The diagonal width, the density matrix, so the width for the x1 equals x2 direction is the first one. How uncertain are you about position? The off-diagonal width, which is the x1 equals minus x2 direction, it encodes how uncertain would you be about the position of that particle if you knew everything you could about everything else in the universe. And so one way to think about it is that the wave function of the particle may be very delocalized like this, but as long as different bits of it are entangled with different looking environments, right, then it's the width of the one that's entangled with this environment basis vector is what dictates the distance over which neutrinos will be coherent. Okay, so now let's put our money where our mouth is and try and calculate some of the things, right? So in all these problems, we've got cascading scales of delocalization. Like if we think about beta decay, a nucleon is localized in a nucleus is localized in an atom is localized in a material is localized in my basement is localized in the solar system. And so the question is always, which one of these localizations do you choose? And the answer I claim is you don't have to choose. You build the density matrix and trace out all the other ones. And so often, but not always, you'll find that it's the more localized scale in the problem. Although Dave and I have some spirited disagreements about some of this. But often you'll find it's the more localized scales in the problem. In electron capture, it's not exactly clear if that's the case. But at least in beta decays and pion decays, it seems to be. And so if we go through a few of these systems that we've looked at, so in the pion decay calculation, this is the one I did a long time ago. The pion is interacting with gas in air in a beam pipe of a decay region of a neutrino beam. The pion is scattering off air molecules in here, and they're measuring its position with a width which is roughly dictated by the momentum transfer of the scatters. That's causing localization of the pion, and then the neutrino encodes that localization scale as it travels. And so basically every time the pion scatters, its density matrix gets multiplied by, it turns out to be the Fourier transform of the momentum scattering, the momentum transfer distribution. So every time it scatters, it gets localized to about a nanometer in this case. We will probably never observe this effect, right? Because if you calculate the distances these neutrinos from particle accelerators go before they lose coherence, for the normal neutrino delta m squareds, they're like 10 to the 8 kilometers, 10 to the 7 kilometers, right? We can't measure neutrino oscillations over those baselines anyway. If you get exotic heavy neutrinos all the way up to like 100 eV squared, maybe you touch experiments that might plausibly be done. But it's almost impossible to see an oscillation of 100 eV squared neutrino anyway, because the oscillation length is so short, right? So it seems unlikely that the neutrinos from pion decay will ever exhibit decoherence effects in measurable systems. But this, at least I claim, is the way you should be able to predict how far they go before they're becoming coherent. Okay, beta decay. There have been a few experiments that have tried to search for the wave packet size from beta decay. Diabay has a limit on this. And so it's useful to have some kind of calculation to compare to. In beta decay, we have a beta source, there's a nucleus. The nucleus is still there after the decay, which is slightly different to pion decay, because in pion decay, the pion's gone at the end. But in beta decay, the nucleus is still there, so it's one of the things you have to trace out at the end. The nucleons are arranged in the nucleus with some correlations between them, and the nucleus itself may be delocalized to some scale. And if you calculate the off-diagonal width of the density matrix, you get this sum of terms, a term to do with how well localized the atom is, the nucleus is, and how well correlated the nucleons are, with some order 1 factors, basically, which give you something to do with how many nucleons there are. This is kind of a toy model. It's mostly meant to illustrate the scales. It's not meant to give like order 1% uncertainties on the prediction. But the point is, clearly in this system, it's whichever is the smallest out of these localization scales is what's limiting, right? It's 1 over this plus 1 over this plus 1 over this to the -1. So in practice, it's likely the nucleon-nucleon correlations or the nuclear size, which are the relevant scale in this problem to dictate the size of the wave. And so we took that model and then we integrated it over all the damn fission branches, right, in the reactor spectrum. My buddy Josh Fitz knows how to do these calculations. So it integrated over the kinematics and the fission branches and everything of the neutrino producing modes in a reactor to predict what you might see at somewhere like Juno. Juno's got the best hope of seeing something like this, but it looks very difficult. I mean, it looks like you need something like 2 picometer size for this to be visible at Juno, but the scale we're seeing here is more like one Fermi in size. And so Juno is already an almost impossible experiment. No offense. But like this looks even more difficult, right? To see the difference between these different possible incoherents. So we're exploring actually, this is kind of done with a toy model of the nuclear wave function, where we just assume a nuclear size and a certain correlation scale. We're working with Sari Pastori and her group to actually do some quantum Monte Carlo with the real nuclear wave functions to get a kind of quantitatively accurate version of this model, but we don't have that yet. Okay, BeEST. This is an interesting recent result. So BeEST has put out a very interesting result recently, which has generated a lot of interest. So BeEST is an experiment where radioactive beryllium-7 atoms are implanted in superconducting tunnel junctions. This material is tantalum, and the beryllium is implanted inside it. And the beryllium decays by electron capture to lithium-7. The recoil transmits energy into the material. The neutrino goes away. And then by measuring the width of the recoil, they infer a lower limit on the width of the neutrino. No, an upper limit, sorry, on the width of the neutrino, and a lower limit on its wave packet width. And so this is actually the first direct attempt to measure the neutrino wave packet width by measuring the recoiling against it, which it's entangled with. And so we tried to adapt our calculations to this model, to this system as well. This system is kind of more subtle, and we haven't exactly worked out all the details yet. But the main point is there's 2 scales that are relevant here. There's the delocalization of the K shell, where the electron is capturing on the nucleus from. And then there's the localization of where that atom is due to the 0-point energy of all the phonon modes. Now, the phonon spectrum of tantalum is well understood. This is what the phonon spectrum of tantalum looks like. And these are like 10 milli-electron volts scale of energies. And at these temperatures in these superconducting tunnel junctions, there are pretty much 0 quanta in any of these phonon modes, except maybe the very lowest energy ones. So almost all the relevant phonon modes are in their ground state. So the statement we're making at the moment is that the ground state motion of the phonon mode seems to be much smaller than seems to be more delocalizing than the size of the atom. And so we predict that the size of the atom basically is the limiting factor when we trace everything out of the density matrix, although handling the details of the phonon modes is something we're still trying to resolve. But at the moment, we predict 6.2 picometers for the sigma response, which is the prediction that BeEST took from us as to compare to in their measurement. So this is what the BeEST data looks like. There's the energy measurement of the recoil. This is our prediction, 6.2 picometers. The BeEST result is a lower limit. And so this is the lower limit calculated according to the way that we advocate to calculate it, right? This is that equal energies prescription way that I stated I didn't agree with earlier. But if they calculate it the way that we think the limit should be calculated, it's still a couple of orders of magnitude away from our prediction here. But I'm quite excited about the fact that talking to the simple team, the simple people, sorry, talking to the simple people, it seems like Simple may actually be able to access this prediction directly, right, which would be super cool. So that's really exciting. But right now, BeEST is still quite far away from being sensitive to either this prediction or these other possible scales that have been predicted. Okay, so that's the first part of my talk. I said the first 3/4 would be on the standard model stuff. Now we're just going to do a quick bit of discussion about the beyond standard model stuff. I have like 10 more minutes, maybe. Right, cool. Okay, great. So environmental decoherence. So like a lot of us probably these days think about quantum mechanics somehow intrinsically in terms of the many worlds interpretation. At least I do, right? Like everything that happens, and then the universe ends up in a giant superposition, and we're on one of the branches, right? One of the anomalous branches. And one of the reasons that people became much more comfortable, I think, with the many worlds interpretation of quantum mechanics is that this idea of decoherence, that entanglement with unobserved things causes things to behave classically, kind of explains to a good degree why these different Everett branches never come back and interfere with each other, right? It kind of explains why we appear to experience the classical world, because the other Everett branches which are in superposition, right, don't interfere with us because there's so much we're entangled with, right? Before people understood that this entanglement generates classicality, I think people were much more uncomfortable with the many worlds interpretation. And for some people, this seems to be a sufficient resolution of the observer problem in quantum mechanics, this long-standing philosophical issue of like, why do I experience a probabilistic universe rather than quantum superpositions? But for others, and these include some pretty smart people like Stephen Weinberg and Roger Penrose, there remains an observer problem associated with why, even though we're traveling on Everett branches that don't re-interfere, we get these Born rule probabilities. Like, why do we experience these probabilistic outcomes instead of just feeling like we're part of the wave function, like whatever that would feel like? And so Penrose says, like, that there must be some non-unitarity fundamentally baked into quantum mechanics, which can explain this, which actually causes at some level some kind of wave function collapse. And Penrose guesses it's something to do with gravity. Well, he would, right? He won a Nobel Prize for gravity stuff. But like, he guesses it's something to do with gravity. And it's actually not a bad guess, right? Because we know that quantum gravity doesn't respect global symmetries, which kind of means it destroys information in the sense we normally understand it in quantum mechanics. And different ideas about how to integrate gravity into quantum mechanics do give these situations that look like they can kind of remove quantum information from the universe and effectively collapse wave functions. And there's really two leading models for how this might happen, how quantum gravity might introduce non-unitarity into quantum evolution. One of them is through the ideas of quantum foam or space-time foam. This is ideas pioneered by John Wheeler and Stephen Hawking to some extent. The idea here is that the metric of space-time itself, if that's a quantum field, it will have 0-point fluctuations, just like all the other quantum fields. That means the curvature has some 0-point uncertainty. That means also that, like, for some fraction of the time, any given region of space-time will contain a microscopic black hole because the quantum nature of it's fluctuating all the time. And things can interact with those microscopic virtual black holes. And in the process of interacting with them, you will lose quantum information from the system. So that's one way by which a quantum gravity model that we don't have, right? These are guesses, but that's one way by which a quantum gravity model we don't have could lead to non-unitary evolution in quantum mechanics. The other way is advanced by Penrose and Biozzi, and this way is to say that if you have a massive particle which is localized in a piece of space-time, the metric of GR, which is there, is also entangled with it. So a superposition of particle here and particle here is actually a superposition of particle here plus curvature of space-time with it going there, and particle here plus curvature of space-time with it going there, right? Now, the thing that makes that kind of an awkward situation is the curvature of space-time basically dictates the rate that time goes, right? And so in a sense, the direction of time, or the rate that time goes, would itself become something which is in quantum superposition with the mass, right? And if time is running at a different speed, effectively, but I mean, I'm saying it kind of colloquially, but if time is running at a different speed for these two different masses, then their phases can't stay coherent with each other, and they must decohere with each other. And so these are two pictures to understand why ideas of quantum gravity might introduce fundamental beyond standard model decoherence, not just the standard model stuff I talked about before, but a new source of decoherence and information loss. And so if you want to understand these things, you need a way of predicting the evolution of a quantum system, which has not only the normal unitary quantum evolution, but also the disgusting non-unitary stuff that quantum gravity puts in. And so you can do this with the density matrix, and the equation you use is called a master equation. There's a rate of change of the density matrix. This is the ordinary quantum mechanics stuff. This equation with just this piece is called the von Neumann-Liouville equation. Then if you add this piece, which has the beyond standard model stuff, this can introduce non-unitarity. And if you want this to preserve the interpretation of this guy as a density matrix, there's kind of a limited form which this term can take. And this is the general form. You can write it in terms of SUN basis matrices. So you write all the rows of the density matrix as a row vector. And then this will be some coefficients multiplied by some SUN matrices, where n is the size of the Hilbert space. And so basically then you start working out what your favorite model implies these coefficients should be, right? The C's that go in this model. So the Penrose thing, the Hawking thing, whatever. So for the space-time foam models, these aren't very prescriptive because we don't have the complete theory of quantum gravity, but basically the idea is these virtual black holes are sucking quantum information out of the neutrinos at some rate, and you can make some rough guesses of what that would look like. One possibility is that the wave function is effectively collapsed. So maybe the neutrino is absorbed by a virtual black hole and re-emitted in a flavor or a mass basis. Something that's kind of nice is it doesn't matter which basis it's collapsed into. If it's collapsed into any basis, you get an equivalent result for the time evolution. That's called state selection. I mean, probably mass basis is the natural one you would expect this to apply to, but luckily the results don't depend on what basis you choose. The other reasonable guess you can make is that the phase of the wave function is randomized as the neutrino is dropped and re-emitted from one of these virtual black holes. So again, one of the things that's nice here is it doesn't really matter how much you guess the phase is perturbed by. You end up with the same effective model, basically, if you have a phase perturbation effect. So these are two ways of thinking about how quantum foam might be interfering with the unitary evolution of systems. And the theory of applying this to neutrino oscillations is done in this paper by my colleague and friend, Tom Stuttard at NPA. And so this is one of the things we tested for at IceCube, is this kind of coherence loss. Now, for these high energy neutrinos, it's kind of nice. I think it's 10 to the minus 28. Yeah. So one de Broglie wavelength of a 10 TeV neutrino is 10 to the minus 20 meters, right? So you might think this is a crazy fishing expedition. You're never going to see any quantum gravity stuff. But one thing to remember is that it's a 10 to the minus 20 meter de Broglie wavelength. And there's 10 to the 8 meters roughly across the Earth. So you're sensitive in principle to an evolution phase of like 10 to the minus 1 part in 10 to the minus 28, right? So 1 part in 10 to the minus 28 in the evolution phase could well be sensitive to some of these small effects, right? And I'll actually show you that it is sensitive to like Planck scale natural effects in the next slide. But so to do this measurement, you have to predict the evolution of the neutrino across the Earth, accounting for oscillations, matter effects, absorption, and decoherence, and disentangling them all. We measure in IceCube the energy spectrum as a function of the zenith angle around the Earth, right? If you do low energies, like up to about here, up to sort of 100 GeV, then you really have to account for the details of all the standard model oscillations and all their matter effects and everything, and it's very hard to make this kind of measurement. But if you go up higher to this higher energy, the standard model oscillations really get shut off, and so you just have to deal with Earth absorption effects, basically, is the only competing effect. And the cross sections for those are known not too badly. So actually, these very high energies, you have a kind of unique access to the decoherence effects without being interfered with by any of these other things, and also very controllable cross-section uncertainties. And so this is the result that we got. This is the power scaling of the decoherence, which is unknown, but n equals 2 is kind of the sort of generic expectation that most people have. This is the effective decoherence strength parameter that is dictated by the density of the virtual black holes in the space-time foam. The previous best results are these ones from T2K and Minos, and the IceCube limit improves on them by a factor of 10 to the 6. So I think I've never in my life improved anything by a power factor of 10 to the 6. I probably never will again. So I should save at this moment. But anyway, this was a nice result, and this is the one that was on the cover of Nature Physics. Okay, so there's other ways to try and get at this non-unitary effect, and some of them have been looked at by other neutrino physics experiments. One thing that's kind of interesting is if quantum gravity is really collapsing particles down to small spatial scales, then collapsing them to small spatial scales implies, by the Heisenberg uncertainty principle, broadening them in energy. Right? So these processes, what they would be doing if they were happening, is adding high energy components to the momentum space wave function. And by adding high energy components, that's effectively an acceleration. And what do accelerating charges do? They radiate, right? So that actually Penrose claims this is nonsense, and his model does not predict collapse radiation. But if you imagine the model predicted collapse radiation, then you could search for it in experiments like Majorana demonstrator. And who knows whether Penrose is right? I mean, we don't have a model, but he doesn't think that's collapse radiation. I don't know why. But anyway, they looked for this radiation in Majorana demonstrator and this other experiment and did not see it at the level expected by them for a Penrose collapse. Now, to look for the Penrose kind of decoherence in something like IceCube is a bit more tricky, and it's a bit more tricky. This is my last slide, so don't worry. This is ending soon. It's a bit more tricky because in the Penrose case, right, the rate at which the wave function collapses depends on the difference in the curvature of the metric between the two things that are collapsing. Right? So what that means is how quantum mechanically delocalized the particle is on the space-time influences the rate at which the wave function collapses. So it's kind of like a snake eating its tail almost, right? It's like, so in order to predict the rate of the collapse, you need to know the width of the wave function which is inducing the collapse. Now luckily, as I've told you in the whole first half of this talk, we've spent a bunch of time predicting the widths of the wave functions of neutrinos in all these different scenarios, right? So we should be able to, because we can predict the widths of the wave functions we expect for the neutrinos, we should also be able to predict the rate that the Penrose model says they should collapse. Right? And that's what we did in this paper, which we put out this year, actually, 2024, with me and a UTA grad student. This grad student doesn't even work for me. I just stole this paper. But it was kind of fun. It was cool. So we see actually on this plot, this is the required scale of the wave function for these effects to be observable. The green is the standard wave packet separation that I showed you before, right? And so the gray is like where these experiments would have to be sensitive in order to see this. You see nothing is sensitive to that standard model effect, right? Sadly. The Penrose thing adds two new effects: momentum drift at the center of mass of the wave function and also a spatial collapse effect. And I'm not going to go into great detail here, but the interesting thing is that it seems like for the widths of the neutrinos we expect in atmospheric neutrino air showers, the IceCube result probably does rule out the Penrose collapse. But this gray error bar is big. And so one of the things we hope to go back and do at some point is apply our calculations to atmospheric neutrino air showers and get a much better prediction of the widths of neutrinos in those, which we don't have yet. Okay, these are my conclusions. I have a habit of like never reading conclusions in my talks because my talk's always way too long. So thank you for your attention.